All right, hello physical science. We are going to take a look at our ramp problems now. So I've drawn this picture. I highly suggest that you draw the picture too. I have it color coded. I'm going to try to keep the colors nice and color coded. Forgive me if I mess them up. Yeah, I'm talking to you, Cassidy, and who else color codes? Oh, Kaylee, and Jenna K, I think you color coded too, and I feel like I'm missing a few, forgive me, please. All right. So this is video number 2 on ramp problems to go along with Monday's homework here. And we are looking at a ball rolling down a ramp. Not only are we looking at a ball rolling down a ramp, but we are looking at it from 3 different frame of references or point of views. So we are going to add some numbers here to our point of views. Let's get markers out. Our first point of view is one over here. It's in red, and it is my person looking this way. So imagine that this is a glass ramp. I can see straight through this ramp, okay? If I were standing over here and I was looking straight through this ramp as the ball is rolling down, all I would see is literally the ball going down. That's the only thing I would see. Because I'm looking straight through, I'm not seeing it going like this. I can only see that it's going down. I may be able to tell that it is moving further away because it may be getting smaller, but it's just really going to look like it's falling down right off the top of the ramp. Okay? If we look at our second point of view, this is the one in green. If I am laying under this glass ramp and not getting squished by it, and I'm looking at the ball rolling down the ramp, all I'm going to see is this. All I'm going to be able to see is that the ball is rolling across, because it's not going to look like it's getting any closer to me or it's going to hit me. It literally is just going to look like it's going across. I wish I could show you, and I can't, really. This is the best way I can describe it, and I need you to believe me and try to imagine it yourself, okay? The last point of view is in purple here. Yes, that's purple. And it's if I were standing, looking at the ramp like it was a demonstration, like you're at a museum looking at a piece of artwork. Okay, and for this one, I am going to be able to see the ball going across and down. All right, because I am outside of it looking at the whole big picture so I can see everything that's going on. It's going to be very important for us to remember as we are solving these problems. So, the first question I want to ask you, and let me put some values in here, is we are going to solve for one of these displacements, okay? So over here, I'm going to say that up and down, this is going to be 2 meters. All right. Over on this side, I'm going to say that my purple side is going to be 3.5 meters long. So my actual ramp, 3.5 meters going down, 2 meters tall. However, I do not have this third side here. Why did I label it as an X? I labeled it as an X to try to keep things a little bit more organized. Okay? This, if we're looking graph style, is my y-axis. This would be my x-axis. All right? And this, you could say, is my y plus my x-axis. That's going to come in handy here. So I'm going to actually take a second to write that down. All right, that's going to come in handy. So I want to first solve for that x-axis. All right, how are we going to find that displacement, that x? Well, we're going to use our Pythagorean theorem. All right, so we're going to get out a new board here. Move one out of the way. Fresh one down. All right. Now my a squared, I'm going to use my 2. Plus my b squared, which I do not have. That's my x-axis, remember. But we do have our c squared, which is at 3.5. All right, let's do some math here. 2 squared is easy. That's 4 plus b squared equals 3.5 squared should give you about 12.25. All right. Now we need to get that b alone. How do we do that? Going to subtract the 4 from both sides. All right. It's going to be b squared equals 12.25 minus 4 is going to be 8.25. However, this is still squared. So we do need to square root these, which is going to mean b is equal to 2.9 meters. Now, how can we double check that answer? There's a really simple way to just kind of check yourselves. If we remember from math class, and we're using the Pythagorean theorem, if you've done, I'm not sure if you've done that yet. I think if you're in algebra, you've definitely done that or are going to be doing it soon. This side and this side should never be longer than our hypotenuse. Our hypotenuse should always be the longest side. So we said that this is 2.9 meters. 2.9 is less than 3.5, so that's probably a good answer. It's a quick way to just check yourselves. All right, if you have any questions on how we did the Pythagorean theorem, please make sure to type it into the Google Sheets. All right. Now, we're going to do some frame of reference problems in solving for velocities here. So, we have all of our displacements, but now I want to know the velocities of the 3 different frame of references. Okay, now this is going to be interesting. I'm going to give us a time here. My time is going to be 2 seconds. Let's do something simple. All right, my time is going to stay the same for all of my velocity problems. Okay? The only thing that's going to change is my displacements. We know that this displacement is the shortest and our hypotenuse is the longest. That means the shortest side is going to have the slowest, the fastest time. Shorter distance with same time, it's going to be fast, right? Same time, longer distance, probably going to be the slowest, right? Because it's got the same amount of time, but it's got a faster distance to travel. So we're going to test that theory here in our problem. So we are going to find the velocity of the 3 different types. I'm going to try to keep this color-coded here. All right. So we have our displacement for our red one, which is 2. 2 meters. Displacement over time, which is going to be the same, 2 seconds. And that one's really easy. That one's going to be 1 meter per second. However, this is a velocity, so we need to add a direction. Now, technically, if we remember from that frame of reference or that point of view, it looks like the ball is just going down. So, this is going to be the down direction, or if you want to relate it to our river problems, that would be south. Okay, that's where it gets a little confusing. Now, our green frame of reference is when you're lying on the ground. Okay, we calculated that the displacement for that is 2.9 meters. So 2.9 meters over 2 seconds is going to equal, do some calculations here, and that should be 1.45 meters per second. And that is going to be, since I'm only seeing it go across, that's just going to be labeled as across. However, if we were relating it to our river problems, since we're moving this way, that would be east direction. All right. So we have our red, our V sub y. Forgot to label these for you guys. Sorry. Got too absorbed in the colors here. Got our green, our V sub x. And then we got our purple, y plus x. Why am I labeling them like that? It's really going to come in handy later, you guys. Make sure you are taking a second to add in those labels. I know I forgot. Sorry. All right. The last one we had that the hypotenuse, or purple, or y plus x, is 3.5 meters. That, again, is over 2 seconds. And that's going to come out to 1.75 meters per second. And this would be labeled as, since we can see it going across and down, as across and down. So just like how we labeled it x plus y, we're literally keeping the same labels as our y-axis plus our x-axis, which are down and across. Now, if we were relating this to like traveling down a river, that would be in the south easterly direction. All right. So river and ramp problems are very similar to each other. It really helps to draw out that basic picture and to make sure that we are really looking from the correct frame of reference. Okay? Make sure you do your labels, color code if you want, if it helps. And good luck on your homework problems, you guys. I will talk to you on Wednesday.